Okay, so then the last question, I'll let you try this one, see which numbers you can come up with. This time I'm asking you, what's the angle if I know the arc length is 3 centimeters and the radius is 10 centimeters? Okay, so in radians is the measurement that I would like. So use radians in your answer when you come up with this. It's actually way easier to answer this question in radians too. Okay, so all we're going to do is manipulate that formula, A equals r theta. So I know that the arc length is 3, and I know that the radius is 10. So theta must be equal to 3 over 10, or 0.3 radians. Okay. So arc length is one of the big applications of radians. For example, you probably won't do this in high school physics, but angular velocity, the number of rotations per minute something makes. Like you might say a wheel is turning at 10 degrees per second, something like that, right? 10 degrees per second means you're going to need to make a conversion into radians in order to figure out how far that wheel is actually rolled on the ground. Because how far it rolled is the same as the arc length. So units of measurement are easier to deal with radians. A lot of questions that come up where spinning wheels are involved, radians just make life easier to work with. Okay, so that's one big application why you would want to use radians. There are many other reasons, but so that sort of ends our discussion on radians. We're going to take a look now at angles in standard position. So here's the idea. You could draw the same angle. So this angle is the same all the way through. We could put it in any position we like, and it's still the same quantity. So we're going to just go over some terminology here for how we're going to deal with angles in a standard position. Okay, so the first thing, I'm good at dropping my pen today. The first thing is we're going to deal with the angle itself. So what we call this piece up here, we call this piece the terminal arm. So what you should think of that is as the angle is raised up to this position, that's where the arm stops. So if the arm is stopped, like terminal, that's the terminal arm. Okay? This arm here, it stays fixed, it doesn't move. This arm here is known as the initial arm. This is where the angle starts, and it grows from there. So those are just a couple of the terms you might hear. When we're going to do standard position, rotation matters. So when we say clockwise rotations, okay, like this, we're talking about a negative angle. And if we're talking about counterclockwise direction, that means now we're talking about sort of this direction. And that would be the positive angles. So, other than those little bits and pieces, you should be familiar with the 4 quadrants. You might already know this as like the cast rule. There's some stuff in Math 11 that you should know this from. All students take calculus, that kind of stuff. We will do a bit of review on this as well. But you do need to know these are the 4 quadrants. We label them 1, 2, 3, and 4. So we're all talking about the same place when we mention them. Okay. So here's what I'm going to do for you. I'm going to show you what 120 degrees looks like in standard position. Okay, 120 degrees, here's the initial arm. And I'm going to plot the angle. It's positive, so it's rotated itself to here in the counterclockwise direction. So how did I know that that's where 120 degrees is? Because I'm the teacher? Any ideas?
More than 90 degrees and it's less than 180.
Yeah, more than 90, less than 180. So I know it's going to be somewhere in quadrant 2. Can we narrow it down somewhere in quadrant 2?
I can't say it's 45, but...
Yeah, it's a little less than half. So we know it's going to be a little bit less than here. where the halfway mark would be. And if you really want to be specific, it's actually 1/3 of the way down to here, because there's 90 degrees. So you can think of this as 90 degrees plus 30 degrees, and that's how I kind of know where that angle shows up. Okay? So let me just show you something here. This is a typical Math 12 thing to do. A lot of students, I'll say, graph this, -5 pi over 4 in radians. And they go, oh, yeah, okay, no problem, Mr. Joyce. Here, hang on. Let me grab my calculator. Okay, so -5 pi over 4. I have no idea what you mean by that, nor do I have any desire to figure it out. So what I'm going to do is I'm going to ignore it, and I'm going to convert it to -225 degrees. And then I'm going to figure out -225 degrees. Okay, it's going to rotate this way. It's more than 180. It's going to be around here. Okay, so that is where -5 pi over 4 is. But there's a whole lot of extra steps in there. And what the tendency is for you right now, if you've never heard of radians before, okay, it's kind of like when you go, say you go down to the States and they're talking speed limits, and you're making those conversions in your head. Because if they're talking miles, we deal with kilometers. Someone's talking about how fast they were driving, and you're trying to figure out, okay, what does that mean to me? Okay, if they're doing 40 miles an hour, that's about 60-something kilometers. You're having to make those conversions, and it's a little more work for you. We actually want to learn to live in radians and work in radians. So the quicker that you stop making this conversion in your calculator, the quicker you learn to actually say, okay, these radians are here to stay, let me start working with them, the easier it's going to get for you. So what I would have done in this situation is I would have worked on it like this, and I would have said, okay, 5 pi over 4, that fraction, it would be handy for me to think of this as -pi minus pi over 4. So can anybody maybe make a guess why I wanted to break it down into those two pieces? Sure, Kara.
You know, -pi over 4 is like the same as 45 degrees.
Yeah, so maybe you remember that pi over 4 is 45 degrees. What's so special about pi? It's half the circle. So in my mind, I'm saying this is a half the circle, and then pi over 4, that's a quarter of the circle. So that means I'm going to go half plus a quarter. So that's where I end up. Same place, but I don't have to make the conversion. So you try these two, 480 degrees, 2 pi over 3. And try to do it without making the conversion. Okay, so for 480 degrees, this is positive, so we're going to go clockwise. So perhaps you thought about it this way, and you thought that's once around, and then 120 degrees. So that's what 480 degrees would look like. 2 pi over 3. How do you explain it without having to convert it into degrees? Sure, Lily?
So it's pi take away a third pi?
Yeah, pi take away a third, so that's half the circle. Take 1/3 of the circle away. Okay? Or you could think of it as 2/3 of the circle. Sorry, 2/3 of the half circle. Is that even more confusing? 2/3 of a half.
Yeah.
Well, anyways, usually in radians, pi is your friend. That's the number you want to work with. Half a circle at a time. So 2/3 of that would be here. Well, maybe it's. I'll make a better picture. Otherwise, it's going to be hard to. So that's probably more like where it would be for 2/3. Okay, so what do you notice about these two angles? So, what did you say, DJ? Somebody's taught you this before, huh? Yeah, they are what we call coterminal. But what I want you to notice is they're the same angle. Different numbers, same position. Okay, so what we call two angles are coterminal if the terminal arm is in the same position. Okay, so that's what we mean when you hear the word coterminal, is they may have different values, but the terminal arms end up on the same spot. Okay. So, what I'd like you to do is I'd like you to find a positive and a negative coterminal angle. one using degrees, like 35 degrees, and one using radians. Okay, so find one which is positive in coterminal, one which is negative in coterminal. Okay, so what's one coterminal angle of 35 degrees? Is it so obvious that nobody wants to put their hand up, or is it so difficult that nobody wants to put their hand up? Who's in the obvious camp? Well, you put your hand up now. Why wouldn't you put your hand up before? Okay, anyways, Connor, help us out then.
395 degrees.
How'd you get 395 degrees?
You added 360.
Good. Right? What's another coterminal angle that would be negative? Pardon me?
325.
Negative 325. So how did you get negative 325 as coterminal? Minus 360. So that's the nice thing about coterminal. If you haven't picked it up, you just do the coterminal dance. Right now you're looking at 35 and you go, now you're looking at 395. Right? If all of a sudden you wanted to go negative, then now you got to go like this. And now you're at negative 325. Okay? So in radians, we're dealing with not 360 degrees, but how much? 2 pi. So if we're dealing with 2 pi, that means, I'll do it on the board here without my calculator. 2 pi, I could write that as 8 pi over 4. Maybe I'll make this a plus sign. So then I'm going to be at negative pi over 4. That's one coterminal angle, which is also negative. And I would have to add 2 pi again to get a positive one. So if I add 8 pi over 4, I end up at 7 pi over 4. So all three angles here are coterminal. One of them is positive, one of them is negative. Okay. So that's how we find it quickly. We add or subtract either 360 degrees or 2 pi. So the reason that we're bringing up coterminal angles is sometimes it's hard to work with an angle like, I don't know, 1300 degrees. You might hear 1300 degrees. I don't know anything about, probably more about 1300 degrees than maybe you would. What I mean is, I don't know what quadrant that's in. I don't know what it looks like in standard position. It's too big for me to work with. What angles do you think would be the nice ones to work with? Can someone like shrink it down and say, well, Mr. Joyce, this would be convenient if all the angles we talked about were, DJ? Somewhere between 0 and 360, right? Those are the angles you've been working with since you were introduced to them. So that's what we call a principal angle. The angle has to be between 0 and 360, or 0 and 2 pi. So, for example, 700 degrees. I don't know where 700 degrees is, but I bet you if I did a quick calculation, and I figured out that this is actually 340 degrees. They're coterminal. 340 degrees I can probably work with. What quadrant's that in? 4, yeah. You might be able to picture 340 degrees better than you can picture 700. So that's why it's nice to find the principal angle. It's easier to think about what position that's in. Okay, what about negative 12 pi over 7? Where would you expect its principal angle? What would you expect? Any ideas? So instead of 360, you're going to add it's a short day today. You guys should still have lots of energy. We're only like 1 block into real math, not 2 blocks. So what's the what am I dealing with? Instead of 360, I'm dealing with 2 pi. 2 pi is less convenient. How about something over 7? What am I dealing with? 14 pi over 7. So 14 pi over 7 would be the nicest way to do it, which means it would be 2 pi over 7, right? And you might not realize it yet. That's quadrant 1 because it's less than pi over 2. So you might not be able to picture it yet because you may not be super familiar with radians, but it'll get there. Okay, so without actually trying to graph this, see if you can find, this is actually an important question for us. This is why I'm teaching you what a principal angle is. You may get something like negative 1750 or 17 pi over 3, and the question may rely on you being able to say which quadrant it's in. Okay, so see if you can figure it out.